Okay. So today we're going to do at least section 12.3. We're going to be talking about another operation that we can do with two vectors. Last time we talked about adding and subtracting them and multiplying them by a scalar or a number. Well, this is in essence the way we multiply two vectors together. All right. So let me just put the definition here of this. If vector A is equal to, let's say, A1, A2, and A3, and vector B is B1, B2, and B3, and again, remember, I'm using those angle brackets to indicate vectors rather than parentheses, then A dot B, so we just say A dot B, is equal to the following. All right, but what we do is we multiply the individual components together and add everything up. So it's going to be equal to A1 times B1, multiplying the first components of them together, plus A2 times B2, the second component, plus A3 times B3. All right. Okay, and what we end up getting then is we end up getting a scalar, which is just another word for a number, okay? There's other terms, so this is called the dot product. Other terms that you may see for this is inner product and scalar product. So scalar product is another term for inner product. Okay. We can also do a dot product in 2 dimensions. Oh, wait a minute. We can't hear me. Oh, boy. Why can't we hear me? Okay. You still can't, can you hear me now? Okay. All right. Well, right now I can't do anything about that, about Brian's not being able to use link. Brian will have to sit with somebody else. I'm concerned about the fact that I heard, can you guys hear me? Okay. Lafayette, can you hear me? Jerry, can you hear me? Okay. I don't understand what the problem is, Jerry, because they can hear me at Lafayette, they can hear me at Eureka. Of course, she can't hear me. Just a second. All right. I know you're. Okay. Okay, they're saying they think it's their problem at Lafayette rather than my problem. But in a way, it is all of our problem because it's delaying me talking about anything further right now. I'm just going to go on and continue here, and you'll follow what I write. Okay. All right, so where was I? Okay, we can do the same thing with two-dimensional vectors. So in 2D, we can write, say we have A is A sub 1, A sub 2. We can dot it with B sub 1, B sub 2, and we just again multiply the corresponding components together and add them together. What we cannot do is dot product something in 2 dimensions with something with 3 dimensions, okay? It has to be the same dimension. Let's look at a couple of examples here. Let's say we have this vector I plus 2j minus 3k, and we're going to dot that with 2j minus k. All right. Now, basically remember what this I, j, and k means. These are those unit vectors going in the x, y, and z direction. So another way to think about I plus 2j minus 3k is this. 1 for the x direction, 2 for the y direction, minus 3 for the z direction, with angle brackets around them. These are both 2 equivalent ways of indicating the same vector, all right? So get used to getting comfortable with both ways of doing it. And then, of course, the second one, notice we do not have an I here, so my I component is a 0. My j is a 2, so that's my y component, and my z component is minus 1. So what I'm really doing here is I'm doing a dot product of these 2 vectors. All right, so we just multiply the corresponding components. So what we have is 1 times 0 plus 2 times 2 plus minus 3 times minus 1, and we end up with 7 as our dot product. Okay. There's some properties of dot products that I want you to be familiar with. And one is this. What if we take a dot product of a vector by dotting it with itself? So basically, A dotted with itself. So they each have the same components. So this is going to be the first component times itself, so A1 squared, plus A2 squared, the second component squared, plus A3 squared, all right? And then let's look at this. Well, Muhat, thanks for coming in. I don't know if there's any advice you want to give them. It is Lafayette. Eureka is fine.
Something on their end.
Yeah, and Jerry has it. She says it is something from their end. Let me type in a message for them since they can't hear me very well. Jerry, I've typed in a question for you there. Do you need our IT person to help you out? She's typing. Okay. So she's finding help from somebody at their school. The answer was.
They cannot hear you, or you cannot hear them?
Well, I never can hear them because they're always muted.
Okay.
Yeah. They can't hear me very well. They say they've got it at top volume and they hear me faintly. But I don't know. Eureka's fine. So she's going to get some help. So they have IT people there also. So hopefully she can get help in-house. Meanwhile, they're just following my written notes. But thank you. All right. Okay. Where are we here? All right. But look at what we have here. Remember this formula that we talked about the other day about the length or magnitude of a vector. The length of a vector is this. It's from the Pythagorean theorem. It's the square root of the squares, the sum of the squares of the components. Okay? So when we dot A with itself, we get the inside of that radical, right? So therefore, what we get from dotting it with itself, and of course another way of saying the length of A is to use those vertical bars, the absolute value bars there. So basically the dot product with itself is equal to that length squared, where I get rid of the radical, all right? Okay. Let's see some other properties here. So that's our first property. The second one is that, well, you know what, if we dot A dot B is going to be the same as B dot A. What?
A2 cubed squared.
That is, thank you so much, Nelson. That middle A is supposed to be a square, not a cube. Thank you. All right. The second product is this property is A dot B is going to equal B dot A. All right, because we can just multiply the components in a different order. Now the third one, before I go into the third one, let me just mention this again. The zero vector in three-dimensional is the vector with 0, 0, and 0 all the way across for its components, all right? So if we take any other non-zero vector and dot it with the zero vector, obviously all these multiplications are going to become 0, so that is equal to the number 0. Another thing is we can distribute the dot product. So A dot, the vectors B plus C, I can distribute that and that gives me A dot B plus A dot C. Okay, just like you distribute in multiplication. And then last thing I want to mention right now is this. If we take a vector and multiply it by a number, a scalar, and dot that with another vector, well, you can just work it out mathematically. What you're going to end up getting is that scalar times whatever you get from the dot product of the two vectors. All right. All right. Now, this is a algebraic interpretation of the dot product, where we talk about multiplying components together and adding them up. There's also a geometric interpretation of the dot product. Okay. What the dot product can provide us with, and this can be very helpful, is it will provide us with the angle that's between two vectors. All right? So, it will give us the angle. Now, we're talking about the angle between 0 degrees and pi, or 0 rather, and pi, or 0 degrees to 180 degrees, between two vectors. All right. And so this is the formula for the dot product that will give us that. A dot B. So certainly I should have put an asterisk over here by the definition of the initial definition of the dot product. Here's another one that I'm emphasizing. A dot B is equal to the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them, where alpha is the angle between 0 and pi formed by the two vectors. If we put them tail to tail. So if we have vector A and we put their tails at the same place, and we have vector B, this angle right here between them, we can call it alpha. That is the alpha that's in that formula there. So what we can do with this formula here is we can just do a little algebra with this and isolate the cosine of the angle on one side. So this formula gives us, when I divide both sides by the magnitudes, I get that the cosine of this angle is equal to the dot product of the vectors divided by the magnitude of A times the magnitude of B. All right? And actually, this formula right here, this that I gave you, it's shown to be true by using the law of cosines from trigonometry. If you're interested, you can see the proof of it in the textbook, all right, how they prove that. So let's look through some examples here using this geometric interpretation. Basically, let's say if we're told that the two vectors have a certain length and a certain angle between them, we can find their dot product. So given that the length of A is equal to 4, and the length of B is equal to 6, and the angle between them is equal to pi over 3, we can now find the dot product of A and B. So we just used that geometric formula there. So the dot product is going to be, we know it's the magnitude of A times the magnitude of B times the cosine of the angle. So we're handed all this stuff on a plate. That's going to be 4 times 6 times the cosine of 60 degrees. So, and cosine of 60 degrees is 1/2. So therefore, this dot product is equal to 12. Okay? Another thing we can do then with this formula is that if we're given two vectors, we can find the angle that's between them, all right? So let's look at, say let's have find the angle between, let's say we have 2, 2 minus 1, that vector, and 5, negative 3, 2 is our other vector. All right. Okay. Well, the formula is this. The cosine of this angle is equal to the dot product of the one times the dot product of the other, divided by the magnitude of the product of the magnitudes here. And the magnitude of 5 minus 3 and 2. All right. And this is just directly from this rewriting of the formula there for the cosine of that angle. All right. So we can just figure this out and we can get the cosine, and then by getting the inverse cosine, we can find the angle. So let's get the dot product. That's going to be 2 times 5, that's 10. 2 times minus 3 is minus 6. 2 times minus 1 is minus 2. All right? And then the magnitude of 2 to minus 1 is going to be what? 4 plus 4 plus 1 under the square root, right? We square all the components, times the magnitude of 5 minus 3, 2 is going to be what? 25 plus 9 plus 4 under the square root. So let's see what we get here. 10 minus 6 minus 2, that's 10 minus 8, so we get a 2 on top. And then 4 and 4 and 1 is 9, so we have the square root of 9, which is 3. And then the other one, 25 plus 13 is 38. And so we can simplify this a little further because of the square root of 9. So we have 2 divided by 3 times the square root of 38. Now this is the cosine of the angle. All right? And on homework or a test, you may be asked just to find the cosine of the angle. So that would be your answer there. However, if we want to find the angle itself, the angle is going to be the cosine inverse of this 2 divided by 3 times the square root of 38. And we all know that cosine inverse has a range of which of the 4 quadrants does the cosine inverse have values for? First and second. It's first and second. Because remember here, remember a smart trig class, or all students take calculus, right? The cosine is positive here, like everything else is positive, but we also want to have it where it has negative values. So in the second quadrant here, the cosine has negative values. So that's why it's the first and second quadrant, which is 0 to pi, or 180 degrees. So anyway, you work this out on your calculator, and it's approximately 84 degrees. That is our angle. Okay. What I want to come up with next then is an important concept that we're going to be using a lot of, at least initially here, and that's the definition of perpendicular or orthogonal vectors. So let me put this down here. 2 non-zero vectors, A and B, are called orthogonal or perpendicular And I'll be using either one of those terms interchangeably, so perpendicular and orthogonal, if the angle between them is 90 degrees. If the angle between them is 90 degrees or pi over 2. And of course that should make intuitive sense here. We have a vector here, we have a vector here where we have a nice 90-degree angle. They are perpendicular to each other. We just have this new word called orthogonal. Okay? So let's see how this is related to the dot product. So recall A dot B, magnitude of A times the magnitude of B. I may not always remember to put all these little arrows on top of things. That can be a little tedious sometimes when you're writing quickly. And remember, it's times the cosine of, in this case, if A and B are, and this is some shorthand that I'm also going to start to use, perpendicular, where you have that upside down T, all right? If they are perpendicular, then their dot product, magnitude of A, magnitude of B, times the cosine of the angle with a cosine of 90 degrees is equal to 0. 0. Yeah, 0. When in doubt, think or visualize that little unit circle with those things. This is 1, 0. This is 0, 1. Minus 1, 0, 0, minus 1, and the coefficients give you the cosine and the sine. So, okay, so anyway, the cosine is 0 there, so therefore the dot product equals 0 if they are orthogonal. So let me write this fact here, and it goes and works in the other direction also. So let me put an asterisk by this fact. Two vectors. And here we're talking about non-zero vectors. For zero vectors, this doesn't make a whole lot of sense. Two vectors are orthogonal if and only if their dot product, A dot B, is equal to 0. So that is a way to test whether two vectors have a 90-degree angle with each other, which we can look at this example here, where, say, you're asked to show that two vectors are orthogonal. And we can do this without trying to draw some picture, all right? So show that the vector 2, 2, minus 1 and the vector 5, minus 4, 2 are orthogonal. I'll start to use that shorthand there. Okay, so what we want to do is we want to look at their dot product and see if it equals 0. So let's look at the dot product. So 2, 2, minus 1, dot 5 minus 4, 2. All right, so let's multiply the components. 2 times 5 is 10. 2 times minus 4 is minus 8. Minus 1 times 2 is minus 2. And those all add up to 0. So without drawing any pictures, we know that those two are perpendicular to each other. Okay. Any questions on that so far? So let's go back here, just maybe kind of a unit circle kind of thing here with our quadrants 1, 2, 3, and 4, where this is 0 and that is pi. So in this quadrant here, the first quadrant, all the trigonometric functions are positive, all right? But when we venture into the second quadrant, as I had just mentioned before, the cosine then becomes negative, less than 0. All right. So the dot product, if we end up with a dot product that is negative, if we end up with a dot product that's negative, then we have an angle that is that's between pi 90 degrees and 180 degrees. Sorry about that. So let me just put this down here. Note the cosine of alpha is bigger than 0 if alpha is between 0 and strictly less than pi over 2. Cosine of alpha is equal to 0 if alpha is equal to pi over 2. And then finally, for that third quadrant, then the cosine of alpha is less than 0, and that's if we're going from greater than pi over 2 and less than or equal to pi, because the cosine of pi is negative 1, so we can include that. All right. So therefore, if A dot B is bigger than 0, the angle theta is an acute angle. Remember that from geometry. An acute angle is something that's less than 90 degrees, okay? All right. Less than 90 degrees. If, of course, we know if A dot B is equal to 0, the angle is exactly 90 degrees. And then if their dot product is a negative, the angle is called an obtuse angle, again a geometric term, and that's where the angle is bigger than 90 degrees. The angle is obtuse, which means it's bigger than 90 degrees. Okay. Okay. We okay with that? Now, given a vector, let me get this slide up here on the screen. Okay, here we are here, and I need you guys to be able to see it. Okay. If we have a, let's just work from this because it's much nicer. Here we have this A, it's in red here. That's our non-zero vector. And we're just going to move it so that it starts at the origin 0, 0, 0. Remember, vectors, they just have direction and magnitude, so we can move a vector around. It's still the same vector, all right? So here we're having its initial point be right there at where the x, y, and z axes meet. And notice then that this vector here actually makes an angle with each of the three positive axes. If what I'm just putting here is I'm overlaying in the, this is the positive x direction. This dark arrow is basically our unit vector I, because I is equal to, remember, I is 1, 0, 0, where that's the x component. Then the one going in the positive y direction, that's our unit vector j, which is 0, 1, 0. And then the one going up in the positive z direction is our k, and that's 0, 0, and 1. And therefore, our vector here makes angles with each of those three unit vectors, all right? And let's call those angles, let's see, what do we have here? We're saying that the angle with the I vector is called alpha. The angle with the J vector is called beta. And then the angle it makes with the K vector is called gamma. All right? So let me put this, and those are called direction angles. So let me just state this. Oh, that's right. Thank you. It's gonna take a while. I'm way over 30, so that puts me at, that puts me at a disadvantage. All right. So therefore, every non-zero vector can be said to form an angle, with the positive x, y, and z axis, or axes rather. Or another way of saying this is or with those nice unit vectors I, j, and k. All right. Now, we've got some terminology here. The cosine of these angles has a name, and it's called the direction cosine. So the cosines of these angles are called the direction cosines. All right. Okay, so let's see what kind of formulas we can come up with here. Let's look at first. Let's have A be our vector, and let's dot it with the unit vector going in the x direction. Let's dot it with I. So what this is A1, A2, A3 dot 1, 0, 0. And when we multiply the components, all we end up getting is A1. Okay? So therefore, we know there that the cosine of the angle between A and I is equal to the dot product, A dot I, over the magnitude of A times the magnitude of I. Well, we've already just now figured out what the top thing is equal to. That's equal to A sub 1, the first component of A. What would be the length of the I vector? 1. It's a unit vector. Its length is 1. So the only thing we really have left over here in the denominator is the magnitude of the A vector. So the cosine of alpha, that is going to be the first component of A divided by its magnitude. So this is the angle, alpha equals the angle with the positive x-axis. And I can do the same kind of thing with J and K. So similarly, so number 2, we know that A dot J is going to equal A sub 2. So therefore, the cosine of beta, when I plug in the formula, is going to be A sub 2 divided again by the magnitude of A. And this is where beta here is the angle with the positive y-axis. And then finally, for the z-axis, we know that A dot K is going to just give us our third component of A, and so we're calling this angle gamma. So that kind of looks like a ribbon, so to speak, in a way. Cosine of gamma then is going to be equal to that dot product, which is just A3 divided by the magnitude of A, and this is where gamma is the angle with the positive z-axis. Okay, all right. So you may be asked to find these direction angles given a vector. So let's just look at an example of that. Example, let's just keep it at find the direction cosine. Okay, I think I figured out the angles too, didn't I? Yeah. And direction angles of the following vector. 1, 2, 3. Okay, that's our vector. All right. So we know that one thing that we need in all of these formulas is the magnitude of that vector. That's what goes in the denominator. So let's figure that out right away. So the magnitude, putting that absolute value around it of that, is the square root of the sum of the squares. So that's going to be the square root of 1 squared plus 2 squared plus 3 squared, which is what? The square root of 1 and 4 is 14. So that's the magnitude of the vector, and we'll use that in all three of these formulas then. So therefore we can so we say the cosine of alpha, the angle with the in the x direction, well that's just going to be my first component, which is a 1, divided by my magnitude, which is the square root of 14. My beta angle with the positive y-axis, its cosine is going to be the second component, which is a 2, divided by the magnitude, the square root of 14. And then the gamma angle with the positive z-axis, its cosine is going to be my third component, which is 3, divided by the square root of 14. So these are the direction cosines. Now to get the direction angles, of course, we go to our scientific calculator and get cosine inverses of all these things. And when we do that, alpha is approximately equal to 74 degrees. And so that's the angle with the positive x-axis. Beta is equal to the cosine inverse of that 2 over the square root of 14, and that's approximately equal to 58 degrees. And so that's the angle that this vector makes with the positive y-axis. And then finally, gamma is the cosine inverse of 3 over the square root of 14, and so that comes out to be approximately equal to 37 degrees, and that's the angle with the positive z-axis. Okay. All right. So we have those nifty little formulas that I encourage you to know how to find. All right. I think this is the projections. The second to last thing that this topic is an important one because with this topic, it's called projections. We can basically see how we can break down a vector into how it's related to another vector plus a vector that's perpendicular to it. And I know that didn't make a whole lot of sense. Let's just go a little bit more systematically here. Projection. Okay. If we have two vectors, and we're talking about non-zero vectors, we'll call them A and B. And let's put their tails together. So using the same initial point. So let's draw a little picture here. Let's have A. Here's A. And then using the same initial point, let's say this is B. All right. So there's an angle between them. And we've just found out how to get, using the dot product, how to find that angle that's between the two vectors. So what if we do this? Let's take the tip here of B and drop a perpendicular down, like a plumb line. Drop that down onto where it's perpendicular to the A vector. All right? So if we have two non-zero vectors, and then drop a perpendicular line from the tip of B to the A vector, from the tip of B onto the A vector. All right. Ooh, and I'm running out of paper there. So let's see here. We drop this perpendicular down. Let's call this point right here. Let's call that point the letter Q. And let's also call this point where we've having the two vectors meet at their tails. Let's call this the point P. Let's just give them some labels. All right. So notice here then, we drop this perpendicular down. We actually can create a new vector as a result of this. If we now look at the vector from the point P to the new point Q that's created by that perpendicular, this has a name, and it's called the vector projection of B onto A. All right, so then the vector from where they join P to where that perpendicular is, Q. Let me put an arrow on top of it. So right here, this right here is called PQ with a arrow on top of it. This vector PQ is called the vector projection. The vector projection of the vector B onto the vector A. One way of looking at this, and I've got a thing to show here. One way of looking at this is kind of looking at it being the shadow of the vector B falling onto the vector A, like at high noon or something, and the light's just coming down. That would be the shadow of that vector falling onto the other vector. All right. So let's look at this thing here. Oh, let's see which one. Vector projections. Here. Okay. What we've got here, let's see if I can move that down a little bit. All right. We've got two vectors here. One is in green and one is in blue. The A vector is the blue vector here. They both start here at the same initial point. So A is this one, B is this one. In this, we can see here obviously that A is longer than B. We're told that A here has a length of 2, B has a length of 1. All right. What we have over here, and notice we have the angle, they're calling it the angle theta, Greek letter theta, between the two vectors. And we have, we can toggle or we can slide what the angle is by sliding this over here. And notice it goes from 0 radians to pi radians, or 180 degrees. So right now we're at what, say roughly pi over 4. That's what the angle is here. This is the perpendicular that's dropped down onto vector A. So we're talking about the projection of B onto A. And I'll write this on the, after we go back to regular notes here. But this is how you write it, and I'll write this again. PROJ for projection, and then the vector that you're projecting onto the other one, you put that right next to it, B, and the one you're projecting onto is a subscript down below. So here we're projecting B onto A. And so we see varying, as we change the angle, the red is our projection vector, the shadow of the vector B going onto the vector A. And of course, as the angle becomes smaller and smaller, the B becomes just about the same as its shadow, as the projection. Now, as we make the angle bigger, so now it's greater than pi over 4, we're heading to 90 degrees. Notice then that the length of the shadow here, the length of the projection is getting shorter. In fact, right here, we have the magnitude here. It's 0.19 times the vector A. We'll go into this formula in just a minute here. I just want to see the visual. And then when we get to pi over 2, which is where they're perpendicular to each other, there isn't going to be any shadow. We're talking about high noon. We've got a flagpole right up there, perpendicular to the ground, right there on the equator. We're not going to have any shadow. Okay, so notice there is no projection there. And then as the angle gets bigger than 90 degrees, so now B is going off in that other direction, notice the projection now going down onto A. We're taking that 90 plumb line onto A. It's now going in the other direction. All right? So A is going in this direction. Now the vector, the shadow, the projection is now going in the other direction. Okay, and so we can keep going to where we get close to pi or 180 degrees, and notice right there when we get to pi, it's going to be basically just the B vector except reverse direction from the A. Okay, it's basically not going to have any shadow. It's just going to be laying on the ground, so to speak. All right. Okay. All right. Okay. So I wanted to show you that little demonstration. So let's get some formulas down here then for this. Oh, let's get the formulas and then take a break. It's time for a break. Now, this vector projection, this is a vector, okay? This is a vector, and because it's a vector, it has magnitude, all right? So the size, or the alternate way of saying it, the magnitude of the vector projection has its own name, and it's called the scalar projection. It's called the scalar projection of B onto A, or it has a second name we could use, or it's also called the component of B along A. All right. If, maybe for a second here, okay, it's on the projector over there. Basically, if we want to look at, if we could divide up this B into a vector that's going in the A direction plus a perpendicular vector that's then going up to the tip of B. This size of this thing would be the component of B if we're just looking at the part of it that's going along the direction of A. So again, it's like the size or length of the shadow that's being formed from B onto A. All right. All right. And then finally formulas, and then we'll take a break. Okay. Since A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle, all right, basically then the length of the projection, let's see what that length of this projection is. Well, let me draw this diagram again. Here we have A, here we have B, and here we have an angle between them. We're dropping down from the tip of B 90 degrees onto A. Now, this is now a 90-degree triangle. This is the hypotenuse right here, and its length is the magnitude of B. Okay, so what is the length of that shadow down there? Well, we're going to use the cosine, which is the adjacent over the hypotenuse. The length of that shadow is going to be the hypotenuse, the magnitude of B, times the cosine of the angle between the two vectors, cosine of alpha. So that is basically the length of the projection. All right, let's kind of write that a little bit differently by using our dot product formula. Our dot product formula says that A dot B is the magnitude of A times the magnitude of B times the cosine of alpha. Well, if I divide both sides of this equation by the magnitude of A, I will have isolated the magnitude of B and the cosine on one side. So therefore, this then gives us A dot B divided by the magnitude of A is equal to the magnitude of B times the cosine. And so this right here is the formula for the scalar projection of B onto A or we could call it the component of B along A. The component of B along A. So I want you guys to remember that. And the shorthand for saying component of B along A is this. COMP for component, B right after it. It's along A, so we put A as a subscript down in between. And then that is equal to A dot B divided by the magnitude of A, which is the same as saying the magnitude of B times the cosine of the angle. But this is the formula that you would use because you don't normally know what the angle is between the two vectors. Okay, let's take a 5-minute break then till about 1/4 after. Oh, it's snowing. A little bit. All right. So let's get started again here. One other thing here we want to get with this projection thing is, okay, we figured out how long the vector is that is the shadow vector from B onto A, all right? But how do we actually represent the vector itself? All we've talked about is how long it is. So we said here the length is A dot B over the magnitude of A. So what about the vector itself? Okay, now A here can have any length. We don't know how long A is. It's just a non-zero vector. In order to figure out the length of this, not the length, but to write this vector here, we know how long it's got to be, but to write it as a vector, what we need to do first is to, first of all, get the unit vector corresponding to A. So the unit vector, of course, is going to be some much smaller vector, presumably, right there. And so that is A, we know to get the unit vector, we divide it by the magnitude of itself, all right? That gives us a unit vector. So this is the unit vector, length 1, that's in the direction of A. It just has a different magnitude now. Ooh, let me, okay. So that has length 1. So to get a vector, and this is a vector, to get a vector that has length A times B over the absolute value of A, we just multiply this amount times our unit vector. So the vector itself is A times B over the absolute value of A, that's its length, times that unit vector going in the direction of A. And I can simplify this a little bit because notice in the denominator I've got magnitude of A times magnitude of A, so I can say that the vector then is A dot B, that's a scalar, over the magnitude of A squared times the A vector. And then this is the formula for the actual shadow vector itself. And then this is the vector projection, because it's a vector, of B onto A. And it has shorthand also for it, just like the scalar one. So the shorthand for this is PROJ for projection, and then it's B onto A, so we write the B right after the PROG, but it's onto A, so we put the A down below as a subscript, and then this vector, the formula for this vector is A dot B over magnitude of A squared times the vector A. And this gives us a vector. The other formula does not give us a vector, it gives us a number. Okay? The component of B along A is a number or a scalar. This is the actual little vector down there that's in the shadow. Going back here to the component, this is a scalar when we come up with it. It's not a vector. Okay. So I want to do an example with these concepts. So what we want to look at here is find basically the scalar and vector projections of B, where B is equal to 1, 1, 2, of B onto A, where A is equal to -2, 3, 1. Okay. All right. So let's do the scalar projection first. And remember, another way for that, to talk about that, is the component of B onto, is it onto or along? Along A. Yeah. The component of B along A. So what's the formula for that? That's A dot B divided by the magnitude of A. Okay, that's our formula. Okay, so we can get A dot B just by multiplying the components together. So 1 times -2 is -2, 3 times 1 is 3, 2 times 1 is 2, and then we can then figure out for the denominator the magnitude of A. Okay, A is -2, 3, and 1, so that we square each component. That's going to be, what, 4 plus 9 plus 1, and simplify this expression, and we get a 3 divided by the square root of 14. So therefore we can write here that the component COMP of B along A is equal to 3 divided by the square root of 14. It's a scalar. Now let's figure out the projection, the vector projection. So let's do the vector part of it. All right. And so remember the formula for that is A dot B over the magnitude of A squared times the A vector. All right. So let's see here. I think we've already figured out what A dot B is. It's 3. We've already figured out the magnitude or absolute value of A. That's the square root of 14. So when we square it, we're going to get 14, right? And then let's see. Then we're multiplying this by our A vector, which is -2, 3, and 1. And we could leave it like this, or we could distribute this with the 3 numbers, and we end up getting, when we simplify, -3 over 7, 9 over 14, and 1 over 14 as a vector. We could write it that way. All right? Oh, yeah, absolutely. Thank you. 3 over 14. Okay, so that's the process of finding this. Now, let's say that what if our vector B that we're projecting, what if B equaled 1, -1, 2? So it's almost like our original B, except we have a -1 here in the Y. Okay, so let's see here. We want to get both of these things. We want to get the scalar part first. So we're going to have A dot B over the magnitude of A. Let's see what A dot B is. So A is -2 times 1, that's -2. 3 times -1 is -3, so that changes. And then we have, then we have 1 times 2 is 2. And then the magnitude of A doesn't change, that's still the square root of 14. So what we get here when we do the scalar part of it is we get a -3 over the square root of 14. Okay, this is going to be a case where the one vector is far enough away that it's going to actually, as I had shown in the picture, let's just do some kind of little diagram here. Here we're doing B onto A. B is more than 90 degrees away from A, so when we drop down that perpendicular, this vector is now going to be going, our shadow vector is going to be going in the other direction. All right, so therefore, that's why we have a minus here now, a negative number in front. So that's our scalar, and as far as the vector part of it's concerned, we just, that's going to be A dot B over the magnitude of A squared times A, and so A dot B, that's going to be -3. Now again, that's going to be 14 rather than the square root of 14. And then my A vector is -2, 3, and 1. All right. Okay. So that scalar projection can be a negative number if the vectors are far enough away from each other in direction. The last topic in this section on dot products has to do with an application in physics. There's this concept in physics that's called work. And work is moving force through a distance. Okay, so we all do work all the time. Climbing up the stairs, we're moving the force of keeping our bodies vertical rather than slumped on the floor, and we're moving it up a set of stairs along a distance, or even just walking from here to there is work. Again, you're keeping yourself vertical and countering gravity, and you're going through a distance. So it's work times the distance. So, and this is going to be a really good product application of the dot product. So work, W, is equal to force times the distance, all right, but the thing is, it's only the component of the force vector that's moving in the direction of the distance that you're going. So we're applying a force along a distance. And we only use the component of force that's in the direction of the distance. We only use the component of force that's along, another way I could say it, of the displacement direction, or the displacement direction. All right, so let me draw a diagram of this. This is going to come right down to the dot product. So say this is our distance here, I'll call it capital D, and we've got a force that's right up here, and it's at an angle to the distance that we're moving that force along, or applying that force to. So basically what we really have here are two vectors. We have a displacement vector moving from here to there, and we have our force vector moving in a certain direction, and we have some kind of angle between these two vectors that I'll call alpha. Now, basically work is the component of force that's along the displacement vector. So basically what we do here is we drop down a perpendicular from the force vector, the tip of the force vector, and we're only going to be looking at the part of the force vector that is that shadow onto the displacement. Well, what's that going to be? Again, this is our hypotenuse, and it has a length of the magnitude of the force. If we multiply that magnitude, that hypotenuse, by the cosine of the angle, we'll get this length right here. So this here is going to be the length of the magnitude of the force times the cosine of the angle between the forces. That'll be the force along our displacement. So therefore, here we have work is force times the distance. Well, the force here is going to be the magnitude of our force times the cosine of that angle between the force and the displacement. And then our distance is just going to be the length of the d vector. That's our distance. However long that vector is, that's the distance we're moving the force along. So what do we have here? We have the magnitude of this vector times the magnitude of the d vector times the cosine of the angle between them. Well, that is just that geometric dot product. This work is equal to our force vector times the displacement vector. Because F dot D is the magnitude of F times the magnitude of D times the cosine between them. So work can actually be very simple to calculate. It's really a dot product, right? So let's say that we're given, let's just look at an example here of this. Say the force F is given by the vector 3, 4, 5. Now, another way of writing this, and you'll see this alternatively, is this. 3i vector plus 4j vector plus 5k vector. These are both equivalent to each other. That's our force, and this force is the force moves the particle from point P, which is the coordinates 2, 1, 0, to the point Q, which is the coordinate 4, 6, 2. So it's moving it along between those 2 points, and we're asked to find the work done. All right. Okay. Now the thing is, we need to have 2 vectors here. We've already gotten the 1 vector, the force vector. We're given that to us. But we're told that this thing moves this particle from point P to point Q. Those are points in space. So we need the displacement vector going from P to Q. Another way of writing that is PQ with an arrow over it. So how do I find that displacement vector? You're making it too complicated. Yeah. Just the displacement vector. The 3 components. How do I find component 1, component 2, and component 3? If we're going from this point to this point, the difference of the 3 components. We take the components of our destination minus the components of where we're starting. Components of the destination minus the components of the start. So in this case, our vector PQ, let's see here, here Q is where we're ending, so it's 4 minus 2, which is 2, 6 minus 1, which is 5, and 2 minus 0, which is 2. Okay, that's our displacement vector. And now, all we have to do to find the work is to do the dot product of F with the displacement vector, and we're finished. So therefore, work is going to be equal to F dot that displacement vector. So that's going to be F is what? 3, 4, and 5 dot 2, 5, and 2. And that gives us what? 3 times 2 is 6. 4 times 5 is 20. 5 times 2 is 10. So I think we have 36. All right? And then with force, let's basically, if the distance is, if the mass is in kilograms, and we're talking about meters per second squared, so the length is in meters, then the force is in newtons. Yeah, okay. Oh, no, I'm sorry. And the force is in newtons. Let's see, did I just do that right? The force, hold it. The force is in newtons. Oh, yeah. The force is written in the term newtons. You can tell I'm not a physicist. And newtons is from mass times acceleration, so that is in the term of kilogram, I believe it's kilogram meters per second squared. So if our force is in newtons, and our distance is in, our length is in meters, then work is in joules. That's the dimension of work, which is a capital J. So therefore, this would be, say we have all those appropriate dimensions, the work would be 36 joules. All right. Okay, so that's the last thing, just a nice application of dot product in physics then. All right. Gee, wouldn't this be a perfect time to stop? Just perfect, right? Oh, I guess so. I guess I'll throw in the towel this time. You know how I hate to do that. You know that, don't you? Right. It does happen, but I think, because I'd end up just repeating everything on the next time anyway, so why bother? So remember, there's no class on, oh gosh, what in the world? It's really coming down outside. There's no class on Monday, so see you on Wednesday. Have a good holiday, I guess, whatever you want to call it. Get home safely. Yeah. What was that? Was that what they were predicting? Flurries? Yeah. Jenna, I think it's a good time to get out running.
I think the weather thing says it's not snowing.
Oh, they tell us it's not snowing.
Yeah.
Oh, okay. Well, then it's not going to snow.
Dry conditions are.
Yeah. Well, you know what? I live in the city. It may be perfectly fine in the city. Who knows? Thank you for catching that one little thing there. Appreciate it. I'm glad you. I know. I'm glad you. No, whenever I mess up with doing something wrong, I want you to tell me whether they can hear or not. It doesn't. It's fine. Yeah.
You said it right. You just wrote it wrong.
I know, and that happens. Sometimes I have this disconnect where I write what I'm going to say maybe 10 seconds from now.
It's a lot harder than an audience to do it in front of people.
It is. See ya.